Okay, everybody, this is section 4.3, multiplication rules and conditional probability. If you remember 4.2, where we did and or logic, where and was intersection of two sets, and then or was a union or a marriage of two sets. So this is the multiplication rules. Two events, A and B, are independent if one doesn't affect the other. If it does not affect the other. So they're independent if one doesn't affect the other. You know, your grade in calculus or your grade in math shouldn't affect your grade in English. They're independent. They each have their separate rules and grading scales. So that's what independent is, where one thing doesn't affect the other. If you roll a dice and get a 6, let's say I roll a dice and get a 6, then the second time I pick up the dice and shake it and roll it again, I get a 3. Whatever I rolled before doesn't affect it. You still have an equal outcome, 1, 2, 3, 4, 5, 6 on the dice. So rolling a dice is independent. Each roll doesn't affect the previous rolls. Even if I got 10 6s in a row, the roll number 11 wasn't affected. You probably say, oh, it'll probably be a 6 again. But in reality, you only have a 1 in 6 chance of getting a 6. So each roll is independent. Drawing a card from a deck may be independent and dependent depending on how you do it. If you replace it, then it's independent. If I draw a card and get a queen, but I put the card back in and shuffle the card, if I draw a queen again, it doesn't matter. It's independent if I have 52 cards still in there. However, if I draw a card and I don't replace it, now I only have 51 cards, so they are not independent. So if I replace the card, they're independent. Drawing a card, second card. So here, replacing the card, right here, replacing the card is independent. But if I don't replace the card, in other words, if I take one out, I only have 51 cards left. It's affected because I can't pick that card again. Don't replace the card, then they're dependent. Replacing is independent events. If I don't replace the card, they're dependent events. One will depend on the other, depending on which card I picked out. All right, so let's see what we have. Here's the rule for independent events. And when you say find the probability of two events are independent, probability A and B, you find the probability A, you find the probability of B, and you multiply them together. So if we look at tossing a coin is flipped and a dice is rolled. These are two different events. So what's the probability of getting a head on, well, find the probability of getting a head on a coin. Anybody know the probability of getting a head when I flip a coin? Just checking if anybody.
50%?
Yeah, 50% or 1 out of 2. You know, the desired outcome is there's only one head on the coin, and the bottom is the total of sides of a coin. There's 2. So, and rolling a 4 on a dice, there's only 1 4 on a dice, but the dice has 6 sides. So rolling a 4 is 1 out of 6, and getting a head on a coin is 1 out of 2. If I want to find the probability of getting a coin, a head, and rolling a 4, I multiply these two together, and on my calculator, when I multiply 1/2 times 1/6, I get 1/12. So my probability is 1/12 for this. So probability of finding or getting ahead when you flip a coin and getting a 4 when you roll a dice. Ahead is 1/2. A dice getting a 4 is 1/6. So you multiply those two together. They're independent. One doesn't affect the other. Flipping a coin doesn't affect how the dice will roll. Okay. A Harris poll found that 46% of Americans say they suffer great stress once a week. If 3 people are selected at random, so here's 3 people, they're blank spots. 3 people are selected at random. Find the probability that all say they suffer great stress, that they all 3 suffer great stress. Well, if to find the probability of all 3, we have to multiply these 3 together. What's the probability that the first person says they suffer great stress? It doesn't tell you in here other than right here. It says if you ask, 46% of the people say they suffer great stress. So we're going to put 46% in here. I'm going to change it to decimal, 0.046. So find the probability that this person suffers great stress. Well, it's 46% because it was told to us up above. The probability that the second person suffers great stress. Well, they're independent. One person's stress isn't going to count as another person's stress. They're independent. They don't matter to each other. So this person is 46% and this person is 46%. So we're going to multiply these 3 together. 0.46 times 0.46 times 0.46. And if we take it to 4 decimal places, we go 0.0973. That's the probability that all 3 suffer great stress at least once a week. And I'll post this video right after I get the class, right after I get the video put together. When an outcome or occurrence of the first event affects the outcome of the second event, it's dependent. So when one affects the other, like pulling a card out of the deck, I have 52 cards. If I pick one, but I don't put it back in, now I only have 51 cards. So probabilities change because I have one less card. So here are some examples of dependent events. Drawing a card from a deck and not replacing it. Having high grades and getting a scholarship. Yes, getting a scholarship depends on whether you have high grades or not. Do you see? If I don't replace a card, then the second card is going to depend on what I got for the first. If I drew the ace of spades on the first card, there's no way I'm going to get the ace of spades on the second draw because I've already drawn it and not put it back. So these are dependent events. If one affects the other. I'm trying to move on. Hang on. There we go. Let's try this one. All they're doing is asking, are these independent or dependent? Drawing a card from a deck and not replacing it. Once again, if you draw it and you don't replace it, it's dependent. So we might want to write that down. If you do not replace it, it's dependent. That means the second card I draw depends on what I drew on the first card. Because once again, if I drew an 8 of hearts on the first card, I can't pick the 8 of hearts the second card because I didn't put it in there. I'm back. Wait. Something happened. There we go. All righty. So I think we did something similar to this. 56% of Americans want to lose weight. If 3 people are selected, here's 3 people. I always put 3 blank spots when I talk about how many people. Find the probability that they all want to lose weight. Well, if 56% of Americans want to lose weight, then find the probability that they all want to lose weight. Well, this person is 56% that wants to lose weight, 56% and 56%. And then just multiply those together. You can also hit 0.56 raised to the 3rd power. When you do that, if I take it to 4 decimal, oh, it says 2 or 3. Let's take it to 3 decimal places, 0.176, if it's 3 decimals. It was 0.1756, so the 4th is 5 or more, so I add 1 to the 5, and I get 0.176. The probability that all 3 lose weight is 17.6% or 0.176. So that's not too bad. Now we need to write these formulas down, especially this one. The probability of A and B, this is when they're dependent, when one depends on the other. The probability of A times, so let me write this down. This means the probability of B given A already happened. So that's what this means right here, B/A. It means the probability of B, that line is given that A already happened, okay? So that's why they're dependent. The probability of B depends on what happened with A. The probability of A times the probability of B given A already happened. All right, so we want to write this, and make sure you write this down so you understand this is the probability of B given that A already happened. So if we look at the word problem here, it says in a recent survey, 33% are overqualified. So I'm just, right here, 33% are overqualified at their job. I'm gonna put it 33%, 0.33 is overqualified. Of these 33%, 24% said they were looking for a new job. Of the overqualified, the 33% overqualified, it said 24%, not 25, 24% were looking for a new job. Okay, if a person is selected at random, find the probability that the person is overqualified and looking for a new job. The probability, so this is how we would write it, the probability that they're overqualified and looking for a new job. Probability they're overqualified and they're looking for a new job. Well, if we go to up here, A and B, we can call this A and B. The A part goes first, or the probability of O times the probability of B given A. B is the J part, probability of J given that they're overqualified. So do you see A and B is right up here? A and B. Call this OA and BJ. A is the O part. And then next is B given A. B is J given O. All right. So once again, let's read. This is the probability that they're overqualified. We already wrote that down, 0.33. I know that one. Overqualified is 0.33. Now, you have to be able to read this. This is the probability that J, what was J? J was looking for a new job. Remember, overqualified was O, but J was looking for a new job. The probability that you're looking for a new job, given, this is the given, that you're overqualified. So, and we already know that 0.24% says that that person feels that he is overqualified and they're looking for a new job. That's the same thing. So that was 0.24, they said. So to find this answer, you just multiply these two together, the probability of O and the probability of J, given that there's a new job. And we're lucky in these paragraphs, they give us all the numbers. We just have to know to multiply them together. 0.33 times 0.24. The answer is 0.079 if I round it to 3 decimal places. When I multiply those together, I get 0.079. So we have to have this formula written down right up here. We have to have that formula written down. All righty. I'm trying to move it down. Hang on. There we go. So let's try this one. Worldwide insurance found 53% of residents of the city had homeowners insurance. So we know homeowners insurance is 53% of our residents. Of these, and that's the key, of these, so it's talking about people who already, only the people who have homeowners insurance, 27% of those also have automobile insurance. So automobile insurance, we don't know what it is, but we do know if you had, if the people that have automobile insurance, given that they already had homeowners insurance, equals 0.27. Do you see? That's what this number is. You see? So first it says 53% had homeowners insurance. Of these, of the people who had homeowners insurance, that's the given. So we have homeowners insurance. We have this. Given that we have homeowners insurance, it's hard to say. I'm saying it backwards, but keep on going. So if of these, 27% had automobile. So this is the probability that someone has automobile insurance given they already have homeowners insurance with that company. So that's what that 27 is. If you read into that paragraph and understand that. So it says, find the probability the resident has both homeowners insurance and automobile insurance. Well, we don't know what A is, but we do know H and A equals the probability of H times the probability of A given H. Once again, if we go back up to the top formula, I mean, that's the formula I'm going to keep on referring to. AB probability of A plus or times the probability of B given A. So A is first, and then A is on the bottom. Same as here. H, in this case, the first one, H is first, and then H is on the bottom. Okay, so the probability of H up here is 0.53 times the probability A given H was 0.27. And we just multiply those two together. 0.53 times 0.27, 0.143, rounded to 3 decimal places. It's 0.1431, so rounded to 3 decimal places, you don't change anything. So you really have to understand that formula and how to extract that data from that paragraph that they give you. Let's try an actual problem now. Let's see this. 3 cards are drawn from an ordinary deck and not replaced. So we're going to draw 3 cards and they are not going to be replaced. So here's the 3 cards we're going to draw. This is letter A. Find the probability of getting 3 jacks. Does anybody know the probability of getting a jack on the first card? What's the probability of getting a jack when you pick 1 card out of the deck?
4 out of 52?
Yes, there are 4. The desired is a jack, right? The top is the desired. There are 4 jacks out of 52 cards. So I have one of those jacks. I'm not going to say which one I have, but I have one. And I throw it on the floor because it says without replacing. I'm not putting it back. How many cards do I have now in my deck?
51.
51. So, and there's only 3 jacks left. We have to pick a jack again. So the next probability, there's 3 jacks left out of 51. I have that next jack and I throw it on the ground. There are only 50 cards left in my deck because I threw 2 of them on the ground. And I have to pick a jack again, but there's only 2 left in the deck because I threw 2 jacks down on the ground. It didn't matter what suit they were, but I did throw 2 jacks on the ground. There's 2 left. So this is the answer. We just have to be able to put that in our calculator. 4 divided by 52 times 3 divided by 51 times 2 divided by 50. And I'm going to hit math number 1 to change it back to a fraction. And the reduced fraction is this. I get a scientific number, but then I go to my calculator, hit math number 1, and I get that. I hope you guys try this along and see if you got the same thing I did. I do want to show that really quick also. Let me show that on my calculator. Give me a second. Well, how come I don't see? There it is. So on my calculators, it was 4 divided by 52 times 3 divided by 52 times 2 divided by 52. 4 divided by, oh wait, those are all wrong. 4 divided by 52 times 3 divided by 51, the card is gone, times 2 divided by 50. There we go. So when I hit enter, I get this number, but I need to change it to a fraction. And don't forget the math button, number 1, fraction, hit enter, and enter again, and it changes the decimal to a fraction. 1/5525. 1/5525. Okay. We could do, let's see if we want to do another one. No, I think we're okay. Let's do one more. Let's do one more. Let's do D. The probability of getting 3 clubs. 1 club, 2 club, 3 clubs. We're going to have 52 cards. And how many clubs are in a deck? Remember, clubs look like this.
I think it's 11.
There's actually 13.
13, okay.
13 clubs, 13 hearts, 13 diamonds, 13 spades. Don't forget, you have that in your workbook. You have to know that. So the probability of getting a club is there's 13 of them out of 52. But I'm not replacing the card. I'm going to throw that on the ground. So there's only 51 cards left in the deck. And there's only 12 cards because I threw one of the clubs on the deck. So then I pick another club, and there's 50 cards left on the deck. If this was a club, there are 12 left. Now there's only 11 left. So multiply all 3 of these together. 13 divided by 52 times 12 divided by 51 times 11 divided by 50. Math number 1. And my calculator says 11/850 when I put that in my calculator. All right. So once again, they're saying do not replace the card. If we replace the card, it'd be 52, 52, 52. And there'd always be 13 clubs because we're putting the card back in. Let's take a look here. I mean, some of these word problems can be a little tricky. Not a lot, but a little. We have 8 flashlight. Wait, 8. A flashlight has 8 batteries. Okay, flashlight has 8 batteries, 5 of which are defective. So it has 8 batteries, but 5 are bad. 5 are bad. How many are, okay, so I'm going to put over here, 5 are bad. How many are good?
3.
Yeah, there's 8 batteries. 5 and 3 is 8. So if 5 are bad, that means 3 are good. So we're going to select 5 batteries at random. So I'm putting 5 blanks there. 5 batteries. It says select 5. If 5 are selected at random without replacement, that means we're not putting the batteries back. We're going to throw them away. Find the probability that all of them are defective. So in the first one, what's the probability of getting a defective battery? We know there's 8 total. And the probability of getting a bad one, well, we know we have 5 bad, or 5 out of 8.
Like 1 out of 3 or 1 out of 2.5?
Well, 5 out of 8 are bad. So
Correct.
That's the probability of getting a bad one. 5 out of 8. Now, though, if I take that bad battery and throw it away, I only have 7 batteries left, and I only have 4 bad ones left because I threw a bad one in the trash. Now, I only have 4 bad ones left. So if I take, so that's the second one. If I take that bad one and throw it away, I had 8. Then I took another one out. I had 7. When I throw that one away, I only have 6 batteries left, and 3 are bad. because I threw it away. So now I have 3 bad trash batteries in the trash. We've done this 3 times. 1, 2, 3. There are 5 batteries left, and there's only 2 bad ones. If I take another bad one and throw it away, there are only 4 batteries left and only 1 bad one. Do you see 1, 2, 3, 4, 5? So once I'm done here, there are 0 bad ones left out of 3. So all 5 are defective. These are how you determine 5 defective. Each of these blanks have to be a defective. There were 5 out of 8 to begin with. We threw 1 away. There's only 4 out of 7 left that are bad. Then there was 3 out of 6, 2 out of 5, and 1 out of 4. And yes, we do have to multiply all of these. And it says round to 3 decimal places. 5 divided by 8 times 4 divided by 7 times 3 divided by 6 times 2 divided by 5 times 1 divided by 4. Math. Oh, you leave it in 3 decimal places. When I put that in my calculator, I get 0.0178. Since 8 is 5 or more, I get 0.018. I have to add 1 to this number because 8, the next decimal is 5 or more. So this is the answer for the probability of getting all defective are 0.018. In other words, 1.8%. So in each of these blanks, you have to understand what you're looking for. A defective battery. We know the total is the bottom. We know there's 8. And then the desired outcome. My desired outcome is to have a defective. Well, there's 5 defective out of 8. Then we throw it away. There's only 7 batteries left, and 4 of them are defective, and so on and so on. Okay, another conditional probability. Once again, conditional probability is this line given. And once again, the probability that a second event B occurs given that the first has occurred. Do you see? This is the probability of B given A already happened. So this is another formula for this. Probability of A and B divided by the probability of A. So do you see on the top it's A and B. The bottom is going to be whatever's on the bottom over here. Probability of A. So let's remember this formula. Once again, it's pronounced the probability of B given that A already happened. The probability of B given that A already happened. The probability of A and B divided by the probability of A. So all these need to be added to your formula sheet. All righty. So these are all the same. Let's read what it says. In a recent survey, 100 people, so there's the total, remember 100 people, and they added these up for us, and there was 50-50. When you add down, you get 100. And then we added down this way, we got 40. Added down, you got 60. When you go across, you get 100. So these they put in there for us. So if it says, find the probability that the respondent answered yes, given that the respondent was female. So this is really important. We want to know everybody who said yes, given that the respondent was female. So the respondent is female. So we're only looking at the female. So this is one way of looking at it. given the respondent is female. So we're only looking at the females because it said that's the given. That's what we want you to look at. What's the probability that they said yes? And it's right here, 8 out of 50. And then, by the way, that reduces. They both divide by 2, 4 out of 25. All righty. So that given means we're just looking at those people. I mean, we can go back up. Let's look at this one. Find the probability that the respondent is male given the respondent answered no. So the given part is they answered no. So we have to look at just the no part. The given tells us only look at the no part. Find the probability that they're male. Well, here's in the no's, these are the no category. So the probability that they're male given that they said no. Well, the probability that they're male is 18. That they said no, there were 60 of them. And this reduces to, they both divide by 6, 3 over 10. 18 over 60 divides in your calculator to 3 over 10. Once again, find the probability that the respondent was a male given that they answered no. So that means we're only looking at the no's. How many males said no? 18 out of 60, which reduces to 3 over 10. All righty. All right, let's take a look at this. So how many more are there? Looks like we got a good amount. Good. We got, well, this is quite a extensive section here. All right, let's take a look here. At a large university, the probabilities that a student takes calculus and is on the dean's list is, so the probability that they take calculus and on the dean's list, so I'm calling C calculus and D dean's list. The probability that they take calculus and is on the dean's list is 0.086. The probability that the student is on the dean's list is 0.34. So we're going to find the probability that the student is taking calculus given that she's on the dean's list. So you got to be able to write that. The probability that they're taking calculus given that they're on the dean's list. So we want to go back up to our formula and look at this. The formula is probability of A and B divided by probability of A. Do you see? The probability of B given A is the probability A and B. I know it sounds crazy. I mean, all these B's and A's. But if you write this down and then say which one's A and which one's B, it's not too bad. The probability of B given A. So here's our formula. The probability of B given A is the probability of B and A divided by the probability of A. That, or did I write A and B backwards? I don't think it matters. Let's see. No, it's probability of B given A. Yeah, I just wrote A backwards right here. Right here. Let me change this. B and A is the same thing as A and B. Okay, so if you notice, A is on the bottom here and A is on the bottom here. So the D part would be the A, and this would be the B. So the probability of A and B, which is D and C, divided by the probability of D. Well, the probability of D is right here, 0.34. The probability of C and D and C and C and D mean the same thing, is 0.086. So using the formula, we just put that in our calculator. 0.086 divided by 0.34. And I get a decimal. It says round to 3 decimals, 0.2529, which rounds to 2.253. 0.253. So you have to be able to read that paragraph. You're going to have these on the test. You have to be able to read that paragraph and translate it. And you have to have these formulas. If they ask for a given, you have to write a given formula. Probability a student takes calculus, given that they're on the dean's list. And then convert that to the formula. All right, here's another one. So before I even begin, I like to do this. I'm gonna add all. Remember, we added up all the totals going across, going down. See, they didn't add the totals for us here, so we have to do them. 20 plus 22 plus 24 is 66. And then when I add going across here, I get 62, if I'm not mistaken. That's not right. 1, 2, yeah, 62. If I go down, so there should be 128 altogether when I add those two up. This is 39, this is 46, and this is 43. When I add all those up, 89, 89, and 41, 28. Yep, they all, when I add them across this way, that adds up to 128 also. Okay, so we put all our totals going across and going down in there. So let's answer some questions. Find the probability of coffee or cookies. Probability of coffee or the probability of cookies. So these aren't and. You notice these aren't and. These are like the other ones. So my question to you is, well, can somebody tell me what's the probability of coffee? Let's see if anybody can tell me what's the probability of coffee.
20 out of 128.
Yes. Coffee. Well, oh, wait. Coffee. The probability of just coffee. You see, it's the probability of coffee or cookies is the probability of coffee plus the probability of cookie. So I just want to know the probability of coffee. Coffee is, there's 66 total coffees. Do you see? If I go all the way across, there are 66 coffees. 66 out of 128. Cookies, I go down this way, there are 39 out of 128 cookies. So let me erase this and just show you. Remember, this is what we did in the last section. So we did this, the probability of coffees. We added 20, 22, and 24 and got 66. Then the probability of cookies. We got 29 and 19 and got 39. Did we add any number twice? Do you see that 20, we added it twice? Because we added it twice, we had to subtract 1. This is from last time. They trick you by putting a last this 4.2 section in here. So the or, if you have the coffee is adding up all the coffees, 66 out of 128. Cookies, adding up all the cookies, 39 out of 128. But we added that 20 twice. So you had to subtract it once. And so now I'm going to put that all in my calculator. 66 over 128 plus 39 over 128 minus 20 over 128. And I'm going to try to get it into a fraction form. I did. And I have 85 over 128. It does not reduce. Okay. Let's see what the next question is. So you got to be careful. They switched us. They switched us. They were doing the ands, and then all of a sudden they did something from the previous section, 4.2. Let me erase this. And go down to the next question. I'm sure it's going to be the new stuff. The next question, if it lets me, is find the probability of T given that it contains candy. Probability of T given that it contains candy. So I want to write that down. So we're looking for the probability of T given that it contains candy. So in this, I mean, the easiest way to do this when we have given candy is we're concentrating just on the candy. When it says given candy, do you see how I circle that? We focus just on the candy. So if I focus on the candy, what's the probability of T? And T is 19 out of the 43. Do you see? This is candy total, 43. And it says the probability that was down here, the probability of T given that we have candy. And the answer is 19 out of 43. So as soon as you see given, you need to circle that given part because that's only what we're talking about. That's what we're talking about, the given part. And you can only pick from there. You can't pick everything like we did in the last. Okay, so here's a different one. Probability T and mugs. There's no given here. So probability of T and mugs. Oh, I erased all that other stuff. So probability of T and mugs. So once again, I had 39 here. I had 46 here. I had 43 here. When I went across in the totals, I had 66 and 62, 128. Probability of T, and, oh wait, is it probability of T and mugs? Yes, probability of T and mugs. So probability of T, or you add them, T and mugs. You look at, here's T, here's mugs. T and mugs, it doesn't say given or anything, it just says T and mugs is right here. 24 out of the total 128. T and mugs is an intersection. T and mugs is 24 out of a total of 128. We didn't count anything twice. We're just using this number here. We didn't count the 46 or the 62. It's just that number, T and mugs, divided by the total 128. And don't forget to put that in your calculator to reduce that fraction correctly. 24 divided by 128, math number 1. And the actual answer that reduces is 3/16. So that was the part 3 of that problem. So each one of these is a different problem. Question 1 was or, where you add the two together. Question 2 was given, where you only circle the given part and then only look at that. And then the third question was and, where and is intersection. Where do the two collide? Where do they intersect at? All right, so this is an easy concept, but it's really, I mean, it's a hard concept to grasp in your head, but it really is an easy idea, concept. Probability of at least or greater than the different inequalities we talk about, less than, greater than, at least. Multiply rule can be used for complementary events to simplify solving problems at least. So what we need to know is this. I think it should be there should be a formula here. Let's see if there's a formula down here. I want to see if there's a formula they told us. Well, there's a formula, but they should have wrote it down for us. They didn't. So I'm going to write it down before we begin. So I'm surprised that they didn't write it down here. I'm trying to erase that. So the probability of at least 1. The probability of at least 1 equals 1 minus the probability of none. So at least 1, if I have at least $1, I could have 1, 2, 3, 4, 5. At least 1 means I have at least 1, but I could have $1 million. You have at least $1. Yes. But I could have $1 million. At least 1 means 1 or more. Another way of saying at least 1 is 1 minus none. 1 minus the probability of none. That's at least 1 means 1 minus the probability of none. I should have spelled none like this. So let's just write this formula down. At least 1, because if I was going to do at least 1, I'd have to do the probability of 1 plus times the probability of 2 times the probability of 3 times the probability of 4, and so on and so on. Or I could just do 1 minus the probability of none, and it would be the same thing. Okay, so in this next example, Neckwear Association reports 3% of its ties sold in the United States are bow ties. So bow ties are 3%, 0.03. So bow ties are 3% of our population. If 4 customers, 1, 2, 3, 4 customers are going to buy a bow tie or are going to buy a tie. If 4 customers who purchase a tie randomly selected, find the probability at least one purchase a bow tie. So it's really impossible to do this unless you do the probability of at least one equals 1 minus the probability of nobody wears a bow tie. No bow tie. You see, at least one is the same thing as 1 minus the probability of none. So I'm going to do 1 minus the probability of none. What's the, oh, this is a tough, this next one's going to be a tough question. Let's see if I can get to it again. Where are we? What happened? How did I lose it there? Okay, so my question is, how do I represent the probability of none, that the person is not wearing a bow tie? What's the probability that the person is not wearing a bow tie? I want to write it down. If 3% of everybody who wears a tie wears a bow tie, how many people do not wear a bow tie? 97%. If 3% wear bow ties, it has to add up to 100%. 97% wear some other tie. Do you see? If 3% wear bow ties, then 97% wear no bow tie, does not wear a bow tie. So in each of these, we're trying to find the probability that they don't wear a bow tie. This one doesn't wear a bow tie, and this one does not wear a bow tie. If they wore a bow tie, you'd put 0.03 in there, but it says does not wear. At least one means 1 minus the probability of nobody wears a bow tie. So I'm going to put this in my calculator. 1 minus, so on my calculator, I'm going to actually 1 minus 0.97. So let me actually come back up here and show you how to put that in your calculator. 1 minus, do you see it was 0.97 to the 4th power? 0.97 times 0.97, but I'm just going to raise it to the 4th power. And this is what I get. You could also do this, 1 minus, then parentheses, 0.97 times 0.97 times 0.97 times 0.97, close parentheses, and you get the same answer. So it's 1 minus 0.97 to the 4th power, but you had to put that in parentheses if you're doing the whole thing with a minus there. So the answer is 0.1147. So probability of at least one bow tie equals 1 minus the probability of no bow tie. And it's 1 minus 0.97 times 0.97 times 0.97 times 0.97. And my calculator got to 3 decimal places, 0.1147, which rounds at 0.115. So just know, and that's going to be on the test, at least one means 1 minus the probability of nobody for that event. And this is another example. This is the last example. So let's take a look at this last, there's 2 examples here. Here's one they did for us, and then we'll look at it. So a coin is tossed 5 times. So you could do this. There's going to be 5 probabilities. 5 probabilities. Find the probability of getting at least 1 tail. Do you see at least 1 tail? It's hard to do that probability. When you see at least 1, know that it's the same thing as 1 minus the probability of no tail. At least 1 means the same thing as 1 minus the probability of no tail. So what's the probability? Well, the probability of getting a tail is 1/2. The probability of getting no tail, the opposite of no tail is heads. There's only 2 choices, is 1/2. 1/2. 1/2. 1/2. 1/2. You see, no tail is the same thing as heads. So you can write it 1/2 to the 5th power. And that's what they do. 1/2 to the 5th power is 1/32. So it's 1 minus the probability of 1/2 to the 5th power, which is 1/32. And when you put it in your calculator, this is what you get. By the way, the line with the on top of it means not. The probability of event equals 1 minus the probability of not happening, the event not happening. Probability of getting a tail is the 1 minus the probability of no tail. So that line on top you can say is no or not. It's no, the event not happening. If the event is tails, then the line on top means no tails. It's not going to be a tail. And the last problem they want us to do, let's take a look. Wait, where did we go? Did I? Here it is. A medication is 69% effective. Find the probability that 12 people take the medication. There's going to be 12. At least 1 person's infection will not improve. It's the same thing as 1 minus the probability that the infection will improve. The infection will improve. And once again, 69% effective. That means 69% will improve. 1 minus 0.69 to the 12th power. There's 12 different ones. So we're going to put that into our calculator. 1 minus 0.69 raised to the 12th power, that arrow up button. Let me show you. Once again, that arrow up button. 1 minus parentheses 0.69, close parentheses, and I want to raise it up to the 12th because I'm multiplying 0.69 times 12, times itself 12 times. And there's our answer, 0.988. 0.988. And we get 0.988. And that's that's it. This is a tough section. You really have to do this homework. You have to have those formulas written down in front of you. If you don't have those formulas written down in front of you, you might have a problem with this. So look at the homework, follow kind of examples that are in this section, have the formulas written down in front of you. It really helpful when you have a formula sheet. I know some of you don't have this formula sheet yet. You need to get it together and practice with it, because a lot of people get this formula sheet together right before the test. And they say, or they don't even have a formula sheet before that. You're allowed to use your notes, but there's too much stuff in this section.
You can post this video.
Be looking for every problem. So you can use your notes on the test, but it's always good to have a formula sheet with everything written down, and it's going to help you for the final. Remember, on the final, you're only allowed 1 page of notes, 1 formula sheet.
Will you post this video later?
Yes, I will. Did I hit stop? No, I didn't. All right, I just hit stop.